So the material that I'll be talking about today is joint work with Kelly Bickle and Joe Sima. For the last couple of years, I've been involved in various projects related to rational inner functions. And I should mention that some of the results that I will use in today's talk are joint with Kelly and with James Pascoe, and also with Greg Neese. Okay, so let me start by introducing the setting that we'll be working in today. So we are going to be considering functions defined on the unit bidisk in the complex plane. And most of the action is going to take place at or close to the distinguished boundary. So I'm setting down notation here as well. I will generically use a point z to denote an interior point of the bidisk, whereas zeta will denote a point in the distinguished boundary. And so unlike in Vavitz's talk, the situation is this. So if we draw the unit bidisk in this way, and the distinguished boundary, the two torus is just this set. So it's a small subset of the topological boundary. We are going to be concerned with function spaces in the bidisk. The main one being H2 of the bidisk. So this is the space of holomorphic functions F with H2 norm finite. This is just as usual. We ask that the supremum over R of radial dilates of R be a finite L2 norm. H infinity of D2, these are the bounded hollow functions. And we will also use the notation A of D2 to denote the bidisk algebra. So these are functions that are continuous on the closure and holomorphic in the bidisk. Whenever I write L2 of mu, this will mean that mu is a positive Borel measure on T2. And so this will just be the space of measurable functions that have finite norm with respect to this measure. Okay, so now that we've set down the notation, let me recall Fatou's theorem for polydisks, which says that one version of it is that if f is in H infinity, that implies that the limit, as r tends to 1, f of r zeta shall denote by f star of zeta exists Lebesgue almost everywhere. So now, once I've introduced this, I can tell you what a rational inner function is. So we say that a function phi in H infinity is inner if the unimodular boundary values, which exist by Fatou's theorem, have modulus 1 at almost every point. That's the usual definition of an inner function. And then phi is rational inner function abbreviated RIF, if phi is of the form Q divided by p, where q and p are polynomials of two complex variables. And so to avoid trivialities, I will typically assume that such functions actually depend on all variables. So let me just give you an example of rational linear function. The monomial z1 times z2 is a rational linear function. Okay. So you might ask, how do we build such objects? Well, we've convinced ourselves that they do exist, but one obvious condition here is that in order for phi to be an inner function, at least if we assume that q and p have no common factors, we need the denominator polynomial p to be non-vanishing in the bidisk, otherwise phi isn't even analytic. So this is an obvious condition. Let me introduce a reflection operation on polynomials. So if we have some polynomial in two variables of by degree m and n, so for multivariable polynomials I will use by degree throughout this talk, then we can set p tilde of z to be the polynomial z1 to the m, z2 to the n, and then times p, 1 divided by z1 bar, 1 divided by z2 bar, and then conjugate of all of that. So this is going to be an analytic function by this double reflection, and then I multiply through by a factor to make this into a polynomial. So let me give you an example. So if I start with the polynomial 2 minus z1 minus z2, then what is the reflection polynomial? Well, it's going to be degree 1 since this polynomial is degree 1 in both variables, I need to multiply by z1 times z2, and all the coefficients of this polynomial are real, so I'm just going to get this expression. And now when I multiply through by z1 times z2, I get 2 z1 z2 minus z1 minus z2. Okay. So I can use this reflection operation to build polynomials out of polynomials. And now the point is this. So this is an old theorem of Rudin and Stout. 65. It says that phi is a rational linear function if and only if phi is of the form e to the I a times z1 to the capital M, z2 to the capital N, and then times p tilde divided by p, where this obvious condition is satisfied. So rational inner functions are not very exotic objects. You can construct them using your favorite polynomial in two variables that doesn't vanish in the bidisk. Okay. So what is the example here? So the example associated with this polynomial would be the rational inner function 2 z1 z2 minus z1 minus z2 divided by 2 minus z1 minus z2. Okay? And if you think about this in the one-dimensional context, this reflection operation is exactly what produces finite Blaschke products. If you take a polynomial in one variable, that doesn't have any zeros in the disk. You can factor it into linear factors, possibly repeated. You perform this reflection operation, that's going to give you exactly the numerator of a finite Blaschke product whose denominator polynomial is the polynomial p that you started off with. Modulo, so unimodular factors. Now, one thing that happens in several variables that doesn't happen in one variable is this fact that if I look at the numerator and denominator polynomial for this function, then they are both 0 at the point 1, 1. So according to the Rudin-Stout theorem or just direct substitution, you can check that this function is actually rational inner. But it is not going to be continuous at the point 1, 1. So this is not a continuous function on the closed bidisk, and this is in sharp contrast to the case of a finite Blaschke product, where if you have a finite Blaschke product, then there's at least some disk properly containing the unit disk on which this is a holomorphic function. So here's a theorem of Greg-Nies, which will be crucial for what I'm going to be doing today. So Greg proves that if phi is a rational inner function, then the non-tangential limits exist unimodularly for every point in the 2 torus. So not just almost every, but there are no exceptional points. The non-tangential boundary values exist at all points of the 2 torus, and they are going to be unimodular numbers. So in this case, you can check, again by hand, that the non-tangential value at the singularity 1, 1 is equal to -1. But like I said, phi star is not going to be a continuous function. So perhaps I should mention that we've recently proved a significant extension of Greg's theorem with Kelly, Greg, and James Pascoe. So we can prove that this is actually true not just for rational inner functions, but for any bounded rational function in any polydisk. So Greg's theorem is actually valid for polydisks of arbitrary dimension, and the same thing is true for our theorem about bounded rational functions. Okay, so one thing that's special about the two-dimensional case is the following. If P and P tilde have no common factors, then essentially as a consequence of Bazoos' theorem, it says that the number of zeros of P on the 2 torus is going to be finite. And in fact, you can write down a specific bound in terms of the bi-degree of P. So in summary, what we're going to be faced with here when we study rational functions in 2 variables are these functions that are really nice in the bidisk, but there may be finitely many points on the 2 torus where numerator polynomial and denominator polynomial share a common 0 without there being some algebraic cancellation. And when this happens, the function is not going to be continuous at that point. And so phi star is not a continuous function on the 2 torus in general. So in order to talk about Clark theory, I need to introduce model spaces. So the model space associated with a rational function phi is k sub phi, and this is the orthogonal complement of phi times h2 and then h2. So this has a reproducing kernel This reproducing kernel is, you can work it out, is explicit in terms of the Cauchy kernel or the bidisk. And you see, when you see this expression, you should realize at this point that this isn't just going to be a product theory, right? Because the denominator here is a product, but the numerator is not. And so it's not just going to be the case that we're going to be able to lift results from one variable and then just directly assume that everything works out just as well. Okay, so one thing that I'm going to note here is that if phi is a rational inner function, then the expression 1 minus mod phi squared divided by alpha minus phi mod squared, well, this is the real part of the expression phi of z alpha plus phi of z divided by alpha minus phi of z. And so this is a positive pluriharmonic function. So it's harmonic along any complex line where it is defined. So positive pluriharmonic function in D2. And so now I can define the Clark measure. Sigma sub alpha, where alpha is some number in the unit circle. This is the unique Borel measure, positive, which has the property that the left-hand side is equal to the Poisson integral of this positive pluriharmonic measure sigma. And so here, this is the product Poisson kernel. So it's made up of two copies of the Poisson kernel. Okay. All right. So we've put down all the definitions that we need, except for one. But before we proceed, maybe we should try to get some feeling for what's going on in this context by looking at an example. And so I was told that I should stick to the large blackboards in the middle. So I guess the definition that you need to remember is right here. Okay. So I think I said a couple of minutes ago that we won't just be able to leverage one variable theory to make progress on these questions in general, but there are some cases where you can use a trick to reduce things to one variable. So the simplest such case is this one. If we look at our product function z1, z2, then this is just on the left-hand side, and the Clark measure definition is just going to be this. And so you can check that this is the Poisson integral of a measure that does the following. So if you pick your favorite continuous function on the two torus, then you can test it against this measure. And what this measure will do is the following. It will evaluate the function at zeta 1, comma, alpha of zeta 1 bar, and then integrate that function with respect to the Lebesgue measure. So the picture, if I draw the two torus as a square and identify it with minus pi pi, and I have the coordinate axes here. And so if I pick, let's say, alpha equals 1, then this is saying, look at the line zeta, comma, zeta bar. That's this line. Evaluate the continuous function f along this line, integrate with respect to Lebesgue. And if you pick some other alpha, you might get something like this. So the support sets of these measures foliate the two torus, and along each such support set, the measure is just Lebesgue. Okay. So this looks nice. So that seems promising. What we're going to do next is we're going to define Clark embeddings. And the origin of this work is a recent paper by Dubtsov in the Proceedings of the AMS, came out in 2020. So I'm going to define a mapping J alpha from a model space into L2 of sigma sub alpha. So the alpha here is the same as the parameter alpha here. And this is done by mapping reproducing kernels to the following expression. And I'm not going to go into the details, but from here you basically do the same thing that Clark did in his original paper. You check that this respects inner products in the correct way, and then you use that these kernels are dense. So this defines an isometry. Now, when dimension d equals 1, this is classical Clark theory. And this is actually a surjective isometry. Okay. So this is suggested that something else is going to happen when d equals 2. And indeed, it turns out that this Clark embedding is not always surjective in two variables or more. And this for us was the starting point. So we saw this paper by Dubtsov, and the example he gave of a situation where you have a Clark embedding that is not onto, is not surjective, was actually a rational inner function. And because we've been obsessed with rational inner functions for several years, it seemed reasonable to try to understand what is going on in this situation. So, oops, that's not what I want to do. I want to do this. So I'm going to use this function. And I'm going to tell you what's going on with the Clark measure in that example. So a couple of properties of these Clark measures, well, they're similar to Lebesgue on T2. So that's because the expression that defines this, the left-hand side, and the expression that defines the Clark measure is going to have a numerator that is 0 for every point, and the set of points where phi takes on a specific unimodular value has that Lebesgue measure 0. So this is true. So the support of this measure, well, you want to say that it's inside of the set of points where the non-tangential values are precisely equal to alpha, and this is a support, so I have to take a closure. And this is true. But other than that, it's not so clear what these measures look like in general. So in fact, you can prove that they can't have any atoms. But let's have a look at what happens in this second example that we looked at. So I'm going to draw the two torus again. So this function has a singularity at 1, 1, which becomes the origin in this picture. And now you can check what the support set for, let's say, alpha equals +1 is. It turns out that it's this diagonal again. And in this case, again, you can sort of work this out by hand, that this measure is of this form, except you now have to throw in a density along this line, but it's some function that's bounded and is fairly nice. Okay? And without telling you exactly what the Clark measure, what the density looks like, if you pick some generic alpha, you're going to see something that is supported in a curve that looks like this. And you can compute what the measure is. But now something exciting happens when you pick alpha equals -1. And what was -1? Well, I didn't prove this, but that's the non-tangential value of this function at its singularity. So again, you can check what the level set is, and it turns out it's the union of this vertical line and this horizontal line. By the way, one thing we can note here is that all of these support sets are going to go through the singularity. But that's, of course, no contradiction because this function isn't continuous. It can well happen that level sets sort of have some point in their closure that doesn't correspond to the actual value that you're examining. Okay. So let me tell you about some facts about these level sets. So the point is that I've worked out some example here, at least in part. And you might say, well, you know, these level sets look pretty nice. They are curves and they have some joint points. But other than that, they look pretty smooth. And actually, that's the content of a theorem I'd like to tell you about. So this is with Kelly and James in a paper that came out last year. So if phi is a rational inner function, then the unimodular level set phi, which I define as the closure of the points where phi attains alpha, that's actually exactly equal to the set of points in the two torus where the numerator polynomial minus alpha times the denominator polynomial is 0. And this set is, of course, closed. So that tells you that the common zeros of numerator and denominator are going to be elements of every level set. So all the level sets are going to pass through each singularity. And again, when d is equal to 2 in 2 dimensions, this set can be parametrized using analytic functions. So away from the singularities, this is of course clear, but because phi has some points where the boundary extension is discontinuous, we can't apply the implicit function theorem globally. But nevertheless, it turns out that in 2 dimensions, these sets can always be resolved into pieces that are parametrized analytically. So as in this case, the blue set is parametrized with a single analytic function, as is the yellow set. But for the red set, you have to do this resolution when you pick the level set apart into 2 components. Yeah. So I'm going to preempt a question that some of you might have saved for later. So this is false if the dimension is 3 or greater. If you go to dimension 3 or greater, these level sets, so this part is still true in arbitrary dimension. But in general, these level surfaces or level hypersurfaces are not even going to be continuous when you go to dimension 3 and higher. And this is an important reason why we focus on the 2-dimensional theory in this case. Okay. So now I'm going to try to build up to our main theorem, which gives a complete description of Clark measures for rational inner functions of degree n, 1. Any questions so far? Okay. So let me formulate a simple lemma, which doesn't need the assumption I'll eventually impose. So this measure may be made up of several pieces, but let's suppose that the Clark measure contains a term that gives rise to the following. So an integral where you fix a horizontal value, and then the measure evaluates functions along a vertical line and then integrates with respect to Lebesgue. So if this is the case, then the corresponding J alpha is not surjective. So this gives a condition when you fail to be surjective. And the argument is as follows. It suffices to show that the bidisk algebra is not dense in L2 of sigma alpha. That turns out to be an if and only if condition. And so the argument here is just that because everything is positive, if you look at the integral of f in this L2 space, well, this is going to be dominated by the full L2 norm with respect to the full measure. Now, if you have a sequence that tends to 0 in this norm, then this term is going to force, and these fn's are in the bidisk algebra, then that's going to force the limit function to be analytic as well. So now you get a contradiction if you pick f equals zeta 2 bar. And this is clearly an element of L2 with respect to this measure, but it's not in, it cannot be approximated in the L2 sense by elements of the bidisk algebra. Okay? So now I'm going to state our positive theorem, and then we're going to explore the ramifications of that result. So the reason I stated this simple lemma before I state the main theorem is that I'm going to restrict my attention to a certain subclass of rational inner functions, but this lemma is valid in general. It doesn't require anything. So now we're going to assume that the degree of P is m, 1. That seems like a major restriction, but you get plenty of interesting behavior in this case already. And I'm going to write polynomial P as P1 of Z1 plus Z2 of P2 of Z1. That just follows from that assumption. And there are some facts that you can immediately deduce about P1 and P2 as polynomials of one variable. So P cannot vanish in the bidisk, and that tells you certain things about the ratio of P1 to P2, and so on and so forth. So one more definition, and then it's time to state the theorem. So we say that alpha is a generic parameter if alpha is not the non-tangential value at some singularity of phi. So there are finitely many singularities of phi. The non-tangential boundary values at these singularities are all unimodular numbers. So you go through that list, and if you pick some parameter in the circle that is not one of these exceptional values, then we call this generic. So here's the theorem. So under these conditions, so phi is a degree m1 rational inner function. Alpha is a unimodular parameter, not necessarily generic, and f is an L1 of sigma alpha. Then I'm going to tell you what the measure looks like. So f d sigma alpha looks like this. It looks like integral with respect to over the unit circle zeta 1 b alpha bar zeta 1 w alpha zeta 1 dm zeta 1. So an expression that much resembles what I had for the specific example, except that in general I need to add in some terms with positive coefficients, and then I have these vertical line contributions. So all of these parameters are explicitly expressed in terms of the polynomials P1 and P2 and their reflections. This is a very detailed description of the measures, and this is valid for all integrable functions in with respect to sigma alpha. So W alpha, for instance, let me give you the formula, is P1 squared minus P2 squared divided by P1 minus P1 tilde minus alpha P2 mod squared. And this is a positive quantity. This is bounded. B alpha is a Blaschke product. And these CK alphas are non-negative real numbers. Okay? So this is a structure formula for Clark measures for any degree M1 rational linear function. So as soon as you know what these polynomials are, you can write down the weight, and you can write down a description of the one-dimensional set along which you integrate. And then you might have to pick up these additional vertical lines where you need to integrate with some multiple of a constant multiple times the Lebesgue measure. And so what is clear here is that if a term like this is present, then the corresponding Clark embedding is not going to be surjective. So if we revisit this example, there is exactly one value of alpha for which this embedding is not a unitary, and it's when alpha is equal to -1, and that's the non-tangential value of the unique singularity of that function. Now if phi is degree M1, then there may be multiple singularities. They can have the same non-tangential value. So the specifics of the Clark measure for some rational linear function of your choice is going to be fairly complicated. But let me formulate the next lemma. So this is, again, assuming that we're in the degree M1 case. So alpha is generic, happens if and only if all of these CKs are 0. So in other words, the corollary here is J alpha is unitary if and only if alpha is generic. So that explains this counterexample that Dubtsov came up with. He picked the single exceptional alpha for this example, and then you get this level set that splits up like this. It contains a vertical line, and so then it's not going to be giving rise to a unitary Clark embedding. So how do you prove this? Well, I'm not going to give you the proof in detail, but I'm going to explain what the reasoning here is. It's specifically this, that we noted that C minus 1 for this example was, so C minus 1 with this cross, and so the lemma covers that situation and says that the embedding is not going to be unitary. Now let's look at C plus 1. Well, that's the set zeta 1 bar. And so what happens if you look at the function zeta 2 to the k, and here k is a natural number? Well, this function is, for each k, this is a function in the bidisk algebra. And now when you restrict it to this +1 level set, well, you get zeta 1 bar to the k. Of course, the image of zeta 1 to a positive power is going to give you the positive frequencies you need to generate L2. And then restricting zeta 2 to this anti-diagonal is going to give you the negative trigonometric monomials. And then by forming linear combinations, you get something that is a dense set in L2 of this Clark measure. Okay. So I have 5 minutes left, or something like that. Okay. So I'd like to tell you about some further consequences of this work. So here's a theorem which is also from our paper. And it concerns non-tangential boundary behavior of functions in these model spaces. So if f belongs to the model space k sub phi, then we can tell you exactly what, we can write down a formula for this Clark embedding, and it's precisely the non-tangential value of f, xi, and this is for sigma alpha almost every xi in T2. So as an element of H2, of course, each function in the model space is going to have non-tangential boundary values at Lebesgue almost every point. But in this result, we first established the existence of these non-tangential boundary values sigma alpha almost everywhere. And it turns out that the value of the function that you get via this isometry are precisely these non-tangential boundary values. So this is some kind of embryonic form of Poltoratsky's theorem for model spaces. Okay. So perhaps I will have to skip over our applications of this work to a question of Rudin. So there's an old question of Rudin that's around that asks for extreme points for measures that represent analytic functions of positive real part in a polydisk. So in one variable, this is not so hard, but in several variables, it's not known what these extreme points are. But via this Clark measure representation theorem, we can identify some positive pluriharmonic measures that are definitely extreme points and some that are not. So for instance, for exceptional values, you always get the splitting, and so then the Clark measure is not extreme. So perhaps the last thing I should tell you about is an extension. It's a question about extending this theorem to a more general situation. And I should say that this is, in full generality, this is a work in progress with Kelly and Joe, and also John Anderson and Linus Bergqvist, my colleague at Stockholm University. So the thing that's good in two variables is that the level sets that the Clark measures for a general degree mn rational analytic function will be supported on are still these nice curves that are parametrized by analytic functions. It's a little bit trickier to write everything as explicitly as in the degree m1 case. For instance, these B alphas are generally not going to be Blaschke products, they're going to be some algebraic functions. Okay, but the natural question is this corollary true if I go from degree m1 to degree mn? And it turns out that it is not. And I want to tell you about that because it's a nice little application of some previous work of joint with Kelly and James. So the last thing, the analog of alpha generic or rather alpha exceptional J alpha not unitary, this fails in the degree mn case when n is greater than 2, because we can do this. Consider the polynomial that is made up of the factor z1 squared, 1 minus z1 squared z2, 1 minus z1 z2 squared, using a construction with Kelly and James, you can find a phi, such a rational entity such that the unimodular level set corresponding to -1 is precisely the set where this polynomial is 0 and non-tangential value is -1, and where the Clark measure looks like this. So this follows from this our general construction. So this is made up of two pieces, and these curves there are two curves that come together at the origin, like this. And so the embedding is going to be unitary if and only if the image of the bidisk algebra in this L2 space is dense. And it turns out that you can do this, just map these two bidisk algebra functions onto the set. These are elements of the bidisk algebra, and it turns out that they match exactly the negative trigonometric polynomials on these two curves simultaneously. So in this case, you have an exceptional value, but the embedding is still unitary. Okay, so this concludes my talk about degree M1 rational functions. We're working on extensions to the general case, and I hope to be able to tell you about that at some future point. Thank you very much.
Thank you very much. Are there questions or comments?
Yeah, maybe I have one or two questions. First one is that in the case when your map G alpha is not surjective, do you have a guess of what could be the range of the map, or at least in some example? Or
well, so in this example that we looked at, it's sort of clear what happens, right? You're only getting the analytic part of L2 with respect to the Begg measure. So you sort of have a codimension. Well, I mean, it's sort of you're missing the complement of H2.
Okay. And maybe another question, just by curiosity. So. In one dimension, you have this famous Alexandrov theorem that says that in the functions which are continuous up to the boundary are dense in the model space. Is it true in your context, or?
So that's exactly this criterion that the embedding is going to be unitary if and only if that happens.
Okay.
And in one variable, it always happens.
Yeah.
So you're always unitary.
Okay.
And so in this case, it just fails in certain cases, discussed amongst others in this theorem.
Okay. Other questions or comments?
Yes, I think I did not understand why in the main theorem, when all the coefficients ck alpha are 0, why does this imply that j alpha is unitary? I mean, is it obvious or?
No, it is not unitary. It's not obvious, sorry. It's
Okay,
unitary, but it's
okay.
not obvious. Sorry about that.
Okay.
So I try to illustrate that in this example. I mean, there you explicitly see what functions you need to choose in order to obtain all the negative trigonometric polynomials. So here, a further argument is needed. So you need to argue that these weights are reasonable, for instance.
Mm-hmm.
And it turns out they are because you know explicitly what they are. They are bounded above, and so the trigonometric polynomials are going to form a basis.
Okay.
And then by playing around with this representation for the B alpha, you can sort of see that for any negative power, you can kind of cook up a function in the bidisk algebra that maps down to that when you restrict to the support set. So it's not obvious. It's an argument that's required, but it works because we know exactly what these B alphas and W alphas are.
Okay.
That's a very good question. Thank you.
Okay, thank you.
Any more questions or remarks? Well, if not, before going to the spring, to coffee break, sorry, we thank the